If you are looking for a shortcut into the future of hardware, you've definitely come to the right place.
Yeah, absolutely.
Today, we are diving into two massive technology breakthroughs announced late in 2025. And these are really set to define the next era of sensing and intelligence.
And these aren't just, small updates. They are entirely new capabilities.
Totally.
What makes this so compelling, I think, is the contrast. We're looking at two completely separate tracks of innovation here.
Okay.
So on one hand, you have the ultra-small, these new, unbelievably pure light sources at the nanoscale coming out of the University of Cambridge.
And then on the other hand, we're talking about the ultra-large, a technology that can turn entire rooms, offices, hospitals, you name it, into intelligent, predictive environments.
That's the one, the new Spatial World Model from Fujitsu.
Right.
And our sources suggest that this dual focus, it's signaling something bigger, a kind of hardware renaissance.
Hardware renaissance. I like that.
So the mission today is to really get our heads around how both light and, well, space itself are becoming smart. Programmable, even.
Okay.
We want you to consider how these advances are redefining what we can sense deep inside matter and what our environments can predict about what we do next.
That's a massive mandate. Okay, let's unpack this. And we're going to start at the smallest possible point. Nanoscale lighting.
The tiniest piece of the puzzle.
When I first read about this Cambridge work, the initial finding, it felt almost like a contradiction. They created functional LEDs, they call them LN LEDs, using a material that is, by its very nature, electrically insulating. I mean, that's like trying to run power through rubber. It just shouldn't work.
It's the material science version of an impossible problem, isn't it?
Right.
I mean, for years, the rule was simple. If a material can't conduct electricity, you can't really make an effective electrical device out of it.
So these lanthanide nanoparticles were perfect for emitting pure light, but they were just
Electrical dead ends, exactly.
So how did they crack that? How do you power an insulator? I'm guessing it wasn't just, cranking up the voltage.
No, not at all. They didn't try to force the current through it. They found a way to go around the problem.
Okay.
They used energy transfer. They attached these very specific organic molecules to the surface of the nanoparticles. And these molecules act like, well, the researchers call them molecular antennas.
Molecular antenna. I like that analogy. It's almost like they built a tiny wireless charging pad right onto the nanoparticle itself.
That's a fantastic way to put it. The antenna molecules, you see, they're great conductors. Unlike the core, they capture the electrical charge. Now, here's the crucial bit of physics. When these antennas get that electrical energy, they jump into a very specific high-energy state. It's called a triplet state.
And what does that triplet state do?
It allows for an incredibly efficient energy handoff. Think of it like tuning two instruments at the exact same frequency.
A resonant.
Precisely. The energy from the excited antenna molecule transfers almost perfectly to the lanthanide ions inside the nanoparticle core. And that efficiency number is the other shocker here. It's over 98%.
98%.
Yeah. And that huge tuned energy transfer is what makes those lanthanide ions light up and emit that near-infrared light.
That efficiency is what really elevates this from a neat lab trick to a genuine breakthrough.
It is.
And the light itself has some pretty special qualities, right? It runs on low voltage.
Yeah, around 5 volts, yep.
And it's spectrally pure. What did that mean in practical terms?
Purity is everything here. When we talk about spectral width, we mean the range of colors in the light.
Okay.
Standard LEDs, even quantum dots, they have a wider, sort of fuzzier emission. But the lanthanide light, because of its quantum properties, is incredibly sharp.
More stable.
So less noise, more signal.
Exactly. Zero interference, which means much greater clarity.
Okay, let's talk applications. What does that pure near-infrared light unlock for us? The source has really leaned into the biomedical side. Oh, it's a game changer for medicine. The Holy Grail has always been imaging deep inside the body without surgery.
Right.
And near-infrared light, especially in what's called the second near-infrared window, or NIR2, has this amazing physical property. It can penetrate biological tissue much deeper than visible light, and it does so with way less scattering.
And less scattering means clearer images.
Precisely. You shine visible light on skin, it just bounces off everything. It scatters. Anything below the surface is just a blur. NIR2 light passes through more cleanly. This is huge for, say, non-invasive tumor detection or monitoring blood oxygen deep inside an organ in real time, or even for light-activated therapies where you need to hit a tiny target deep inside the body.
And what about outside the body? That narrowband emission sounds perfect for communications.
Absolutely. Optical communications, fiber optics, that sort of thing, they all depend on stable, clean signals.
Here.
If your light source is super narrow, you can pack more data channels closer together without them bleeding into each other. It promises systems with much higher precision and potentially a big boost in data throughput.
Now, let's put on our critical hat for a moment. This all sounds amazing, but if it's so revolutionary, why isn't it everywhere already? You mentioned the external quantum efficiency. The EQE is what, around 0.6%?
It is.
To our listeners who follow this stuff, 0.6% sounds, well, pretty low.
And that's a crucial question. It really is. It's all about context. Yes, 0.6% is low compared to a commercial OLED display, which can be over 20%.
Right.
But you have to remember where this material started. Before this antenna trick, the EQE of an electrically driven device made from this insulator was 0.
Okay, so 0.6% isn't the finish line, it's the starting pistol?
Exactly. It's the difference between impossible and now we have a path. The researchers already have a roadmap to improve it.
So refining the antennas, tweaking the structure.
All of that. The challenge has shifted from can we do this to how high can we push the efficiency?
Which brings us to the other hurdles. Beyond efficiency, you have manufacturing at scale and, for medical uses especially, meeting those incredibly strict standards for safety and biocompatibility.
That's the long road ahead. When you blend organic and inorganic materials like this, proving it's stable and non-toxic inside a human body for years, that's a massive regulatory and engineering challenge.
Sure.
But what's so fascinating here is it's this new way of thinking. Blending of materials at this tiny scale to unlock capabilities we all thought were impossible. It opens up the whole periodic table for engineers again.
That's the potential for deep sensing light. But now let's zoom all the way out. Let's talk about how the space around that light is also becoming intelligent.
A pretty dramatic shift in scale.
It is. We need to go from the nanoscale to the spatial scale, where whole environments are getting a cognitive upgrade.
Yes, let's talk Fujitsu.
This brings us to the Spatial World Model, or SWM. This is a technology that's designed to turn these big, messy, physical spaces.
An airport terminal, a construction site.
A busy hospital floor, right, into intelligent environments that can actively understand and even predict what's going to happen next.
It's like giving the room a central nervous system.
Yeah.
And a memory. The SWM tracks everything, people, robots, equipment, and understands their relationships in real time.
So how is this different from, the advanced camera systems we already have? The ones using computer vision to track things.
That is the critical distinction. Traditional methods try to stitch together video feeds at the pixel level, and that is incredibly difficult and computationally expensive.
And fragile, I'd imagine.
Very fragile. If a person turns or a robot goes behind a pillar, or even if the lighting just changes, the system can break. It's constantly fighting the physics of light and perspective.
So the SWM gets around that by thinking more abstractly.
Exactly. Instead of processing raw pixels, the SWM builds a 3D scene graph.
A scene graph?
Think of it like a dynamic blueprint of the space. Every person, every object is a node, and the lines connecting them represent their relationship.
So it's not thinking, I see pixels of a robot. It's thinking, Robot A is 3 meters from person B who is walking towards the door.
That's it exactly. This allows the system to maintain a coherent global state of the room, even if one sensor is temporarily blocked.
And that abstract semantic level of understanding is what allows for the real magic trick here, prediction.
Yes. Because the system understands the relationships and the rules of the environment, it can start to model what happens next. It can anticipate where a person is likely to walk.
Or if a robot's current path is going to cause a problem in, say, 5 seconds.
Precisely.
That kind of situational awareness seems absolutely essential for getting robots out of cages and factories and into the messy real world with the rest of us.
That's the #1 use case. Think about a busy warehouse. Right now, robots either work in fenced-off zones or they have to move incredibly slowly.
For safety.
Right. SWM gives them the awareness for fluid human-robot collaboration. If it predicts a person is about to cross a robot's path, it doesn't wait for the robot's own sensors to see them.
It tells the robot ahead of time.
It sends an instruction early. Adjust your speed, change your path. Proactive, not reactive.
That's a huge safety upgrade. It prevents collisions before they're even a risk. But does that high-level view lose the precision a robot needs for a specific task?
That's a great question. But the SWM acts as the coordinator, the air traffic controller, not the individual pilot.
I see.
The scene graph is perfect for coordinating multiple robots and people. It scales beautifully, it tells a robot where to go safely, and the robot's own local sensors handle the fine details of, say, picking up a box when it gets there.
And what's the timeline on this? Because this feels very practical very soon.
Fujitsu is moving fast. They're doing a public demonstration at CES 2026. That's just around the corner in January.
And what will they be showing?
The real-time coordination and predictive control. And then throughout fiscal 2026, they're planning extensive technical demos to prove it works under all kinds of real-world conditions.
It's incredible. In one deep dive, we've gone from molecular antennas making pure light to 3D scene graphs making smart rooms.
But when you look at them together, you see they really are two sides of the same coin.
Smart materials and intelligent space.
And if we connect this to the bigger picture, the ultimate potential is this future where deep sensing wearables, intelligent robots, and these aware environments all start to converge.
The physical AI and hardware renaissance you mentioned at the top.
Exactly. The next big breakthroughs won't just be new apps. They'll be brand new capabilities defined by the hardware itself, by the physics.
So paint a picture for us. What does that convergence look like in, say, a hospital?
Okay. So imagine a next-gen hospital robot. It's equipped with a sensor using those ultra-pure NIR LEDs. As it approaches a patient, maybe one wearing a deep tissue monitoring patch, the light from its sensor gives this incredibly clear, non-invasive data on, I don't know, tissue health or tumor response.
So the deep internal sensing is happening.
Right. And at the exact same time, the hospital ward itself is running the Spatial World Model.
The SW.
The SWM knows the robot's path. It knows where the doctors are. It predicts when a nurse will approach the bed.
And it coordinates the robot's movements to be perfectly seamless.
Perfectly. The robot isn't just a dumb delivery cart anymore. It's performing real-time deep diagnostics, while the room itself ensures it moves safely and efficiently.
That's the merger of deep sensing and intelligent action.
That's the vision.
A powerful vision, but we have to come back to the challenges. For the LEDs, it's still about efficiency and reliability, right?
Absolutely. The engineering climb there is huge. Mass production, making sure they last for years, and getting those critical safety certifications for use on or in the human body, that process alone can take a decade.
And for the spatial world model, the challenges are less about the tech itself and more about trust.
Yes, exactly. Trust and validation.
Because you're talking about constant environmental monitoring.
You are. SWM faces enormous public trust hurdles. You have cameras and sensors in potentially private spaces, so privacy and data security have to be perfect, non-negotiable.
And it has to be bulletproof.
It has to be. You need to prove it works in every crazy scenario. Smoke, power outages, you name it, before people will bet their safety on its predictions.
So we've journeyed from a molecular antenna making an insulator glow with pure light, all the way to a 3D scene graph turning a room into a predictive agent. It's just an incredible snapshot of where hardware and AI are headed.
It really feels like an inflection point, doesn't it? The physical world is becoming transparent and predictable in ways it just wasn't before.
Right.
We're building devices that can see deep inside the human body with these NIR LEDs. And at the same time, we're building environments that can predict what that human body will do next with SWM.
And that raises a pretty profound question.
It does. As these two layers, deep internal sensing and external prediction, start to merge, how will we as a society define the boundaries? How do we manage intelligence that is becoming so pervasive and so personal?
That is definitely something for you to mull over as you watch this hardware renaissance unfold. Make sure you keep an eye on CES 2026 for those SWM demos and follow the research out of Cambridge as they push the efficiency of those amazing LN LEDs. Thank you for providing the sources for this deep dive.